Hi, I'm Mark Boxer, and you've reached our webinar. You're on our webinar, everything you wanted to know about fiber but were afraid to ask. This is a live webinar, and this is the first in our webinar series for electric co-ops. And we have a ton of content today, and so we're just going to go ahead and get started. We will have time for some questions at the end. But did want to highlight this is the first in a series, and so the first one is primarily fiber focused. We'll have other ones that are going to be focused in different parts of the network in terms of choices of cable and deeper dives into cable and deeper dives into architecture and how to handle things at the home and at MDU. So this is the first of what we think will be a series of a number of different webinars on a variety of different topics, with the primary focus for electric co-ops, but certainly open to others as well. So just a little bit of background on OFS before we get started. For those who are not familiar with who we are, on the left-hand side of the screen, you can see a timeline, and so this timeline goes back through Lucent Technologies, AT&T, Western Electric, all the way back to Alexander Graham Bell. And when I talk about who we are as a company, I like to highlight that we are the fiber optic arm of what was Bell Labs, and so we have as a company just a very rich heritage of innovation as well as reliability, and it is deep into our DNA. And we've been around really since fiber has been around, and as a company we have a global reach. And so we've got numerous plants in the U.S. as well as a lot of operations around the world, along with our parent company, Furukawa of Japan. So you look at the the product and service offerings that we bring they're basically for an entire network. So the little image that we have in the center of the screen shows a hypothetical network where we're starting in a central office. And for a co-op, that could be at a central office, could be at substations, but we basically provide fiber, cable, splitters, boxes, jumpers, and just various devices throughout the entire network to include fiber to the home, fiber to the cell site, and really a wide variety of different fiber optic solutions. So the first part of this presentation, and I'm going to go through this relatively quickly because this is not a deep dive into fiber, but this is a deep dive as to why a lot of people are thinking about fiber and taking fiber. And we've got 5 really pretty strong reasons why we are seeing fiber being deployed into places all over the world and deeper into the networks, especially with the push over the last several years into more and more rural areas. So the first reason is fiber is future-proof. And so, if you compare fiber to copper, if you look at copper has relatively low bandwidth, low distance, high cost per bit, and fiber is everything that copper isn't. So it has very high bandwidth, it can go very long distances, and we'll talk about that because it has very low attenuation. And ultimately, you can pack a ton of signals onto a fiber, which means that your cost per bit is dramatically reduced. And with that, that really has allowed our networks to grow to the point that we are doing all of the neat and wonderful things over them that we're doing today. So if you compare fiber to either wireless or copper, and when I talk about copper, I'm also thinking about coax to a certain extent, although coax has a little bit more capability than copper. But if you look at the just the timeline over the past roughly 30 years of copper versus wireless versus fiber in this graph, the single mode fiber that was introduced in the early 1980s is still viable and compatible today, and we've got speeds of 100 gigabits plus for hundreds and thousands of kilometers. And so the fiber, the basic design is the same, whereas if you would have deployed copper, then we would have gone through phone grade copper category 3, 5, 5E, 6, 6A, 8. And in wireless, we all hear about all the various generations of wireless. And so the main point of this slide is that single mode fiber stands the test of time. And so I am constantly asked, what's next after fiber? And I think the answer right now is, we don't know that there is anything next after fiber. So, if you put in a fiber network, we have a very strong expectation, and this is OFS as a company, as well as, just the people familiar with fiber as an industry, that if you deploy fiber, we expect that these fibers to be, will be around and will be capable for a very long period of time moving forward. So, and that's the reason why fiber is now the core of most phone, cable, and power networks. And so, if you look at the way that a lot of networks are deployed, they're deployed in rings to either nodes, substations, or cabinets, and ultimately go out to individual homes, individual buildings. And if you think about what happened in the 1980s, where we were just first starting to deploy fiber, we were deploying from maybe one part of the country to another part of the country, and in those situations, the node sizes, so the number of customers that we were deploying to at the end of a fiber, was very, very high. And so you basically deploy a fiber to a metropolitan area, and you may have thousands or millions of people on that node. And so what has happened is, we continue to build out fiber. The node sizes continue to fall to the point that fiber is now being built out with node size equal 1, and that means that it's going to individual homes, individual apartments, individual buildings, individual cell sites, and all strange and wonderful things that we're continuing to hear fiber being deployed to. So another question that I get constantly is okay, well, wireless is going to take over fiber, and the answer there, and I've been hearing this now for 30 years, and really, wireless loves fiber, and fiber loves wireless. Together they make just an absolutely fantastic partnership, because wireless, just by definition, doesn't have the bandwidth that fiber has, and fiber, by definition, doesn't allow the same mobility that you get with a mobile device. And so, as our networks continue to build, and as we continue to do more things on our mobile networks, then that partnership will absolutely continue, where we will see more fiber going to support mobility applications. So if you look at a mobile network, a lot of people don't know, but now, the vast majority of, with mobile networks, there is a fiber ring that connects, the various cell towers together in various configurations. And really, the only thing that is wireless is the last area, the last distance from your phone to the antenna. And in the vast majority of networks, and certainly as we continue moving forward into 5G, then this is going to become even more the case. So, what about 5G? Really, there is no fiber without 5G. Or there is no 5G without fiber. So if you look at where we are today with a typical 4G network, so this graphic came from a paper that the Fiber Broadband Association had put together, and it looked at how today's 4G network can, you can use one antenna, and that one antenna may cover many city blocks. Whereas if you look at what is going to happen between the 4G network and the 5G network, that one 4G network that is operational today may need up to 60 small cell sites for 5G in order to deliver the promised bandwidth with 5G. So really, there is no 5G without fiber. And to kind of reiterate this point, to cover just the top 25 U.S. metropolitan areas, that's going to require roughly 10.5 million small cells, and it will be a multi-decade build out. So fiber really is the most future-proof thing that we're aware of as a communications medium. Second reason why fiber attracts. So residents and businesses decide where to locate based on the quality of broadband. And we are seeing this every day. And at first it started in metro areas, but now we're hearing in relatively rural areas as well that fiber increases home value. And even more importantly, the lack of fiber can render an area less attractive. And so that is one of the reasons, especially in rural areas, that we are seeing more of a push towards moving, getting fiber deeper and deeper into rural areas. Because there is there's a drain going on where we see people going from rural networks to urban networks. And one of the things that can help stem that drain is just making sure that we have good broadband throughout really throughout the country in both the urban areas and the rural areas. So just looking at the slide, the fiber increases home value. There was a Fiber Broadband Association study that was done a few years ago, and it showed that fiber in your neighborhood raised the value of your home by roughly 1.3%. And once you put gigabit speeds on top of that, then that could add up to 3% to the value of a home. So fiber is simpler, and so you can install one cable versus two. So this really gets back to history. And in the history of networks, we first started with copper networks for our telephone cables, and that's the reason that the networks have grown up this way is really historically. We had copper that was used for our telephone networks, and then roughly in the 70s and 80s we started seeing coax networks for cable TV. But what has happened over the past, certainly I'd say 15 to 20 years, is that the protocols for a lot of our content have collapsed down such that you don't need separate networks in order to deliver all of the content, and you can get all of the content plus a ton more on one fiber that will handle TV, voice, data, and really whatever else we see coming down the pipe. So reason number 4, fiber is easier to install and is less expensive. So the price of fiber, I started working in the industry in the late 1980s, and if you compare the price of fiber from 1990 to really where we are today, it's fallen by roughly 95%. And we expect to see these types of price decreases over time in the technology world, and that absolutely has happened in fiber, and the consumer ultimately becomes the beneficiary, and it enables us to deliver many more services and hopefully a better quality of life because of this. So if you take into account now the cost decrease of fiber, and you compare deploying metal cables versus fiber in a building, with all new buildings now, we very strongly believe all new buildings need fiber, because if you're putting in copper and coax today in buildings, you are putting in basically a medium that is it's obsolete today. So if you're going to do that because you have done that in a building before, just make sure that you add some fiber along with it. The fiber is very inexpensive, and can make sure that your building is prepared for the future. So the final reason why fiber is that fiber is less intrusive and easier to install. So this, a lot of people have seen this picture before, or a picture like it, and it's the coil of cable that, in this case, it's coax that the cable guy left. So if you compare that to a fiber, and so you can see that in this picture, you've got a fiber on the right-hand side of the screen where it's actually in the grooves of the mortar. And so I'll let that linger on the screen and maybe show the laser real quick to point that out, because it may not be obvious because the fiber is so it's so hard to see. So fiber has become less intrusive and easier to install. Fiber is rugged and reliable. So the same fiber type that can go into those 90-degree angles in the mortar between the bricks, a different version of that can also be tied into knots and stapled. And so now for the first 25 years to 30 years of fiber, people were concerned that fiber was delicate, and so we took great care just to make sure that we didn't expose fiber to stresses and strains beyond what they could do. And we still want to do that, especially in the backbone part of the network. But as we start going out into the edge and we start going into individual homes and buildings, there have been new fiber types that have been developed and new casings, new cables for the fiber that allow fiber to be, as or more rugged than metallic cables. And so we are seeing these be deployed, by the millions in homes around the world. So moving on to light as a communications method, light has been used as a communications method literally for hundreds of years. So you can think about smoke signals, you think about using Morse code with light. So the topic, or using light as a communications method, is not a new thing. And actually using and guiding light is a relatively old concept. So Jean Daniel Caladin and John Tyndall in the 1800s demonstrated that light could be guided within a liquid. So the famous demonstration is you put a bucket on something and have light shine into the bucket, and then let light go out, and actually the sunlight, you can actually see the sunlight being guided by the water. And the reason that this works is due to something called reflection, or total internal reflection, which is something that is the baseline of how all fibers work that we'll talk about in a little bit. And then there was also a guy named William Wheeler who invented light pipes for home lighting using reflective pipes. And it's similar to some of the concepts that are used today for interior car illumination. So I would like to give a shout out to Larry Johnson of Fiber Story for this and the next slide regarding fiber history. And so if you look at some towering figures in optical communications, Theodore Myman invented the first laser. Charles Cowell proposed practical application of optical telecommunications, and Kekmar and Schultz, doctors Kekmar and Schultz, developed the first low-loss optical fiber back in 1970. And again, this slide came from Larry Johnson as well. So the concept of using light for communications and developing fiber, it has been around now for close to 50 years. And what we have seen, over the last several decades is that the lasers were invented in the 60s, fiber manufacturing techniques were invented in the 70s, and to a certain extent the 80s. And it's been kind of interesting because the industry actually had to develop its own manufacturing techniques. It had to develop its own standards, its own testing techniques, and basically an industry was developed from scratch. Single mode fiber, as I mentioned earlier, was invented in the 1980s, and really from the 1980s till now, the designs there have been some tweaks on designs, but and certainly major quality improvements and process and cost improvements. But the fundamental design of single mode fiber is not really that much different today than it was when it was first invented. And since the early part of the 2000s, we have seen fiber being deployed in volume, literally around the world. But there's still a long way to go. So the light spectrum, fiber uses light for communications, and one of the most important questions, and a very important question from a safety standpoint, is just what is the color of light? And so with the color of light, actually, we can see the visible spectrum. But everything in fiber optic communications, and I'll go ahead and highlight this again with the pen, is that, at least I think I'll highlight it with the pen. So these are the visible colors, but with the majority of wavelengths that are on typical fibers, these are all outside of visible light. So we actually can't see these, and so it's very important to make sure that you're using proper eye detection, because we actually cannot see the light that is being transmitted down fibers. So heading into the next slide, optical fiber is the fastest pipe available. And so this is, looking at the anatomy of fiber. And so I would like to stop before we go further and just see if there are any questions. And if there are any questions, please feel free to go ahead and submit those. We've got John Lawrence on the webinar, and he's taking the questions, and then we will address those as we continue on, at the end of the presentation. But back to back to fiber, it is the fastest pipe available, and the light travels in the core and really bounces off the cladding, and this process is called total internal reflection. There is the glass, or there is a core, there is a cladding, and both of these are made of glass. And then there is also a plastic coating that is on the outside of the fiber to protect the glass. And one fiber, as we mentioned in the presentation, can handle hundreds and millions of telephone calls all at one time. So the fundamental mechanism that we use with fiber to guide light is called total internal reflection. And it uses something called Snell's law. And Snell's law from high school physics deals with the differences of index of refraction of two different materials, and at what angle light will either reflect or refract out of the glass. And so what fiber designers do is they will add certain amounts of different materials in a fiber in order to change the index of refraction in order to guide the light to make sure that it stays in the cable or in the fiber as it's going down, as it's going down its path. So, and as I mentioned a little bit earlier, there is a critical angle, and what this critical angle is where, and jumping to the laser tool again, we can see you go to the critical angle, you'll bounce off, and then if you go beyond the critical angle, the light will go through, and it will actually, instead of reflecting, it will actually refract out of the fiber. And so that results in loss. So a little bit deeper dive into fiber structure. The fiber structure has a core, and the core is the center of an optical fiber. And for the majority of co-op type applications, this core is going to be in the 8 to 9 micron range, although common telecommunications fibers will go anywhere out to roughly 50 and maybe even larger cores. And then the cladding, which is completely silica. So in the core, there are dopants that change the speed of light. And when we go out to the cladding, then this is still pure glass, and this is typically pure silica, and that is pure glass to around 125 microns. And then there are a couple of layers of coatings on the outside. And so just going back through this again, you've got the core in the middle, the cladding at this 125 microns, and then a couple of layers of plastics on the outside. And so one thing to mention, we will talk about standards a little bit as we head through. And the main standard for single mode fiber that is used in typical co-op applications is called ITU G.652. And so this is a starting point, but we'll also talk about some additional standards that are often included in the fibers that are being deployed by co-ops. So, looking at the types of fibers, I've mentioned the term single mode, and that is contrasted with multi-mode. So, so a single mode fiber carries a single mode of light. And so the core is around 8 to 9 microns. And this is a look at the index of refraction profile. And so, this is 125 microns, and the core, you can see that the index of refraction is raised at the center, and it looks kind of like a square wave. And this allows one mode of light to go through. With multi-mode, multiple modes of light can travel through this glass. So you can see that there's a mode in the center. You can also see that there's a mode on the outside. And actually, when you count them up in many multi-mode fibers, you can see up to 17 different modes that can travel different paths down the glass. And what happens with a multi-mode fiber, because you've got multiple modes of light traveling down at the same time, this can actually cause the the light to get to the end of the fiber at different times, causing something called dispersion. And it means that multi-mode fiber actually has less capacity than single mode fiber. And we'll touch on that as we continue through the presentation. So the core with single mode only allows one mode of light, and single mode fiber eliminates the modal dispersion that I just talked about a little while ago. It also has very low attenuation, and low attenuation is basically loss. And it, this is typically 0.2 to 0.3 dB per kilometer at 1550 nanometers. And so single mode fiber is used for most networks over around 2 kilometers or about 6,500 feet. And so the vast majority of networks with any length beyond that are single mode. So back to some more geometry. We talked about the core a little bit earlier, so let me go to the core again. The core is in the center. There is a cladding, but if we expand the core, so that's what this arrow is about, to kind of take a closer look at what happens in the core. There is a physical core, and this physical core is approximately 8 microns, but it turns out that some of the light in the core actually travels outside of the physical core. And this area where there is still some light, but we're outside of the physical core where the dopants are, this area is called the mode field diameter. And so sometimes you see the term mode field diameter on fiber specifications, or hear fiber people talking about mode field diameter. And so this is the difference between core diameter. Core diameter is the physical diameter where the dopants are, but mode field diameter is actually where 95% of the light is carried, right outside of the core. So in the core as well as around, the outside of the core. So as we start to get into some of the properties of fiber, attenuation is the loss of light power over distance, and it's typically measured in dB per kilometer. So that's one of the things. So when we talk about fiber specifically, the vast majority of measurements in fiber are made using the metric system. So we'll talk about dB per kilometer. When we get into cable, it really depends on what country we're operating, because in many situations, we'll have people who are much more comfortable with English units than metric units. And so when we get into cable, sometimes customers are more comfortable with English units. But when we talk about fiber specifically, it's almost always we're going to be talking about measurements in terms of metric units. But to give an idea about how pure fiber is, and just the low level of loss, with 0.3 dB, that corresponds to roughly 93% of the power going through the fiber. So you're relatively low loss in fiber overall, very much in comparison to really all of the other communications media that are out there. So what actually causes this loss? There are different attenuation mechanisms. So there are 10 different mechanisms that will cause attenuation. So one of those, and we'll talk about these in some more depth as we continue on during the presentation, but the first one is absorption. And so absorption is where the glass itself or the dopants will actually absorb light. And so the light goes in, but they're absorbed by the materials. So another attenuation mechanism is scattering, and this is a very important one. And it's done by really the glass and the impurities. And so you'll see some light that is scattered back. There are also a couple of different other types of bending mechanisms. One is called micro bending and one is called macro bending, and these deal with the fiber being bent in some way that it was really not designed for originally, and going beyond, so the light goes beyond that critical angle and the light escapes. And we'll talk about these in a lot more depth. So some intrinsic attenuation is caused by something called Rayleigh scattering, and that is basically caused by variations in the density of the glass. So as the light is traveling down, there is some light is just because of the structure of the glass itself. the light is kind of bounces off the various molecules, and most of it is transmitted through, but some of it is actually transmitted back. And for those of you who are familiar with the term OTDR, this is an optical time domain reflectometer. And the OTDR uses the fact that a fiber scatters a certain amount of light backwards in order to be able to measure the loss of the fiber, as well as being able to identify very tightly where a potential problem source of attenuation could occur. So one other thing that's also interesting is that the attenuation is proportional. We've got a little just a little formula down here. It's proportional to 1 over the wavelength to the 4th. So as in general, as the wavelength as the wavelength gets longer, then the attenuation will drop to a certain extent. And then once we get into the 1600 nanometer range and beyond, things start reversing a little bit, but that is a curve that holds through where optical fibers typically transmit. So we've talked a little bit about scattering. This is microbending. And so microbending is if you have a point stress on the outside of the fiber. So the rectangles here are a fiber. So we've got light that's bouncing around, and then if for some reason there is a lateral stress on the outside of the fiber, then this will cause the light to go beyond the critical angle, and that will cause something called a microbend. And then there's also something called macrobending that we'll talk about in some more depth. And these are actually 2 different mechanisms. So with macrobending, if light goes around a tight bend too tightly a lot, you'll have a very large optical loss. But now there are bend optimized single mode fibers or bend insensitive fibers that basically allow the signal to keep going. And you may recall a little bit earlier in the presentation, I showed some fibers that were stapled and tied into knots. And these fibers and these applications have special designs to help minimize or help reduce the amount of microbending that occurs. And so the amount of macrobending that occurs. And macrobending is important. So this is a graph of what happens when you have macrobending. And so this on the x-axis is our wavelengths, and on the y-axis is loss, and the various curves, the blue, the magenta, and the yellow curves. These are curves as fibers are bent more tightly. And as the fibers are bent more tightly, and as the wavelengths get longer, then the bend loss goes up to the point that, especially if you're using a standard fiber and you deploy it at a 5 millimeter bend radius, so a 10 millimeter diameter, then you could see a tremendous amount of loss to the point that with a typical fiber to the home network, you could actually lose signal. And so this is why we as an industry developed some fibers that we'll talk about in just a second, and these are bend insensitive fibers. But this challenge becomes even a bigger challenge with some of the next generation protocols that we're seeing come online literally right now. So if you look at the protocols that are typically used, especially in co-op networks for fiber to the home, the vast majority of them are still GPON, although we're hearing some deployments of 10 gig EPON, which is also called XGS-PON. But what's key about these is that the old protocols operated at 1490, 1515, and 1560. The new protocols are operating at longer wavelengths, and so what that is resulting in is more bend loss. So going back to the slide just a second ago, if I can do that, you'll see that as the wavelengths get longer, then the losses get higher. And so, with the next generation PONs, the wavelengths are definitely getting longer, which means that the losses are going to get higher, which means we need to pay attention to it. And the way that we pay attention to it is with ITU G.657, which is a different standard, but connected for bend insensitive fiber. So I just gotta note that we won't be able to answer the questions on the webinar as we're not getting them live, but we will be able to put together an answer back to everyone through email, and we'll also be sending a link to everyone in the broadcast, so you'll be able to see the recording as well as some of the answers to the questions. So so continuing on with the presentation, the bend insensitive fiber standard is G.657, and what we're seeing is a little bit of, and actually we'll show you kind of where these are used in different parts of the network. So different fiber types do different jobs, and in the network core and drop, and so especially with co-op networks, you can see this is an ADSS network and this would be a trunk. So we would use a fiber that is compliant to 652. But then a lot of fibers that are being developed now also have some bend insensitivity in them, and to the 657A1 standard. So I didn't really go through this in depth, and let me spend just a couple minutes more on this slide. So 657A1 we use primarily in bend challenged outside plant cables. So primarily for drop cables, but also for micro cables and some very, very high density cables, we'll use 657A1. So for most connectivity applications, so this is when we start getting into cabinets and those kinds of things, and you'll have illustrations of these as we go back to the next slide. Then this is the A2 standard, and as we go into the home, into the drop, then this will be, this is the 657B3 standard. So this slide shows you graphically, what we were showing earlier in the last slide, just with some words. So the network core and drops uses the combination of 652D and 657A1. And then cabinets, boxes, enclosures out in the network use 652D and 657A2. And then in homes and buildings, and so these are where you have the fibers that are going along the ceiling or being stapled to the inside the home or tucked underneath the vinyl siding. These are 657B3. So different fiber types do different jobs. So one thing that makes bend insensitive fiber special is that it does have a different index of refraction profile. So I showed earlier with single mode fiber that it's basically a square wave, and a little bit of light goes outside of the core to form the mode field diameter. With bend insensitive fibers, this is actually, these profiles are not exact in terms of just in terms of the the size and shape, but they are, you can see with bend insensitive fibers in general, they are going to be more complex. And that complexity is caused by using different types of materials to guide the light in different ways. And so, it's not that we just put a different, different coating on a fiber. Actually, the fundamental glass is manufactured in a different way. So one thing that's also very important, especially for new network users, I hear this question very, relatively often, is that different fibers, they question, can different fibers from different manufacturers be spliced together? And the answer to that is absolutely. So G.652, G.652D and G.657 can be spliced together. So if you've got a G.652 from someone and a G.652 from someone else, you can splice that together. If you've got a G.652D and a G.657 from somebody else, you can splice those together. But fibers that have different mode field diameters may show something called a gainer. And a gainer, and I'm not going to go into the depth with the gainer, but this is basically an artifact caused by an OTDR, and these don't affect network performance. But the one thing I would say is don't splice single mode fibers to multi-mode fibers together. That's something that we typically don't do. You'll see a lot of loss, and they typically multi-mode and single mode fibers actually transmit on different wavelengths. So back to some of the intrinsic attenuation mechanisms. Talked about absorption at the very beginning. So natural impurities, especially OH ion, so the hydroxyl ion and or water in the glass absorb light. And so 1 part per million of this will cause 40 dP per kilometer loss at 1383. So this is actually a pretty big problem. And you can actually buy fiber that still absorbs a lot of light. And so this is something to be aware of, especially in times where there is an industry shortage and you've got people from around the world selling different types of fiber. So the reason that this is important is that if you look out at the optical spectrum and how the optical spectrum has been used over the last multiple decades, basically what has happened is through the decades we've seen that the first 30 years focused on 1310 and 1550, and let me pull out my pointer. The first 30 years focused on 1310 and 1550. And over the last 30 to 40 years or 30 years, we've seen different protocols that have been introduced. And these protocols basically use the entire optical spectrum. And so if you've got absorption that is occurring, and let me go to the next slide because it'll clarify this a little bit more. In fiber manufacturing with a conventional single mode fiber, if you've got the OH ion in the glass, if you've got some of that, as we mentioned earlier, what is it, 1 part per million can cause 40 dB of loss. So if you've got just a little bit of OH ion in your glass, you can see some very high attenuations, and this primarily occurs in the 1383, 1400 nanometer range. And so what manufacturers have done over time is that they have just improved the manufacturing process. So you start out with the conventional fiber that you can actually still buy today. So we just caution to be careful about the fiber that you purchase. There are manufacturers that sell something called low water peak fiber and zero water peak fiber. So OFS's all-wave products they're named all-wave because they have very low loss across the entire optical spectrum. And so these are also known as zero water peak, essentially because there is no increased attenuation due to the water peak relative to what you would see with period. So moving on from attenuation to dispersion, different components of light travel at different speeds in the fiber. This can cause some signal distortion. So with digital signals, if you start out with an input pulse that looks, like, and let me go ahead and pull out the pointer again, that looks like this. As it goes through, distance, that pulse can spread out. And the more that pulse spreads out, then the less bandwidth that you have. So dispersion is basically taking a signal and degrading the signal. So that's a digital example, and in an analog signal, you see the exact same thing, where maybe you had an input signal that looked one way, and then it comes out and it's distorted in some way. It may be maybe elongated. And so dispersion is what you will cause. In addition to attenuation, dispersion is actually looking at just the form of the pulse as it goes through the fiber. So there's something called chromatic dispersion, and chromatic dispersion is due to just the speeds of the different colors of light and how they travel through the different components of a fiber. And then there's also something called polarization mode dispersion. And so polarization mode dispersion is a pretty interesting thing. So one thing about chromatic that I didn't mention earlier, this is typically frozen into the glass at manufacturing. And so, and it's also a product of the design of the fiber overall. So there's not that much that you do to change chromatic dispersion. Polarization mode dispersion as a manufacturer, if you manufacture everything perfectly, so you've got two fibers on end in this graphic. And so let me just highlight this. So this is a perfect fiber, and you'll see as we do this little animation with the perfect fiber, there are two polarizations in a fiber that travel down the glass at the same time. So light is an electromagnetic wave, and as an electromagnetic wave, it has two components, and those two components in a perfect fiber go down the fiber at the exact same time. But if you now have a fiber that has a little bit of eccentricity to it, you can see that this fiber has a little bit of eccentricity to it. So it means that everything's not perfectly round. Then what you're going to see here as I animate this is that these two polarizations are going to travel down the fiber actually at different speeds. And the delay time it takes that results from these two polarizations traveling down the fiber at the same time is called something called PMD. So as a manufacturer, we are very concerned about PMD, and there are many different causes of it. There are both intrinsic causes and extrinsic causes. And this becomes more important as we get into networks that go above roughly around 10 gigabits per second. So typically below 10 gigabits per second and with relatively short distances, it's not an issue. But as you go above 10 gigabits per second and as you go longer distances, then it actually does become a bit of an issue. So the way that we as a manufacturer, we fix this is we do something special in the manufacturing process called spinning. And what this does, we actually spin the fiber during the process, and what this causes to happen is the glass, since it's molten, actually becomes normalized, and basically it becomes rounder as we spin in both directions. It just makes everything a lot rounder, and as everything is rounder, then that means that we have much better PMD associated with the fibers. So that's a little bit about optical performance. As we get into mechanical reliability, especially for a lot of electrical co-op networks, is a very important, thing. And one thing to note is that glass is stronger than steel, and the coating performance is actually an integral part of the fiber strength. And when designed and installed properly, then fiber can last for decades, and we now have seen that. So we are at the point that fiber has been deployed in aerial networks for probably 35 to 40 years, and some of those networks are still operational. Now the fiber that is in those networks is nowhere near the quality of what we make today, but even the stuff that was made decades ago has lasted, and we believe that the quality has gotten better over the last several decades. So how pure is OFS glass? I typically ask this of an audience, and the reason we have the Powerball picture here is that the raw material impurities are measured in parts per billion. So if you know the odds of winning Powerball, it's somewhere in the north of 1 in 250 to 300 million. And so you're roughly 3 times more likely to win Powerball than you are to find impurities in the fiber core. And that's in the raw materials. And after we finish processing it, then the fiber is even purer once we go beyond there. So, the purity is very important, and we consider that to be a hallmark of OFS glass. And so that really shows itself when we get into looking at synthetic silica versus natural quartz. So the fiber on the left-hand side of the screen is synthetic silica, and this is the process that OFS uses. The fiber on the right side of the screen actually uses natural quartz for the cladding of the fiber. And so you can see just different, and these are both cleaved and then acid etched with hydrofluoric acid. And so what you can see is the fiber on the left is pristine. The fiber on the right has a number of different pits and imperfections and those kinds of things. And in general, if I'm building a network, I'm going to want my network to look like the stuff on the left as opposed to the stuff on the right. So with aerial co-op networks specifically, there are a lot of aerial networks, and so limiting fiber strain drives all mechanical reliability calculations. And as manufacturers and designers, when we give out numbers, what we are doing is we are limiting the long-term strain on fiber to basically negligible crack growth. So we'll give a maximum number. We'll say that the cable can't go beyond 600 pounds or 1,000 pounds or 1,200 pounds, depending on what the application is. But that number is typically related back to allowing no more than around 0.2% strain in the fiber for negligible crack growth. And so this serves as a cable limitation for the maximum rated cable load for ADSS and maximum installation cables for installation tension for duct and underground cables. And fiber has been very well known for outstanding reliability due to this limitation, due to the fact that the manufacturers very strongly limit the application space. And so the manufacturers are doing their jobs correctly, and the installers and the designers are doing theirs, then we end up with very reliable networks. And that really has been what has happened in the history of fiber. So there is something that's kind of interesting called dynamic fatigue. And this is just a little graphic of what happens and to illustrate dynamic fatigue. So even though we try to make everything pristine, all glass has flaws, and 100% synthetic silica reduces the number of flaws. And so, but what we are interested in is how do these flaws behave in the presence of stress due to either installation, weather, or other conditions. And so this is measured by a parameter that's called the dynamic fatigue parameter, or ND. And so we've got just a little graphic of this with a fiber with lower ND, lower dynamic fatigue on the left, and a fiber with higher dynamic fatigue on the right. And assuming, and this is a very hypothetical, it's just a hypothetical illustration of what dynamic fatigue means. And so assume that we installed these cables, and the flaw that was there is at 100 kpsi. And so if you go 8 years, and maybe you went through some ice storms that were beyond what you had predicted, then maybe there's a residual amount of strength left on the low dynamic fatigue of 82, whereas on the higher you still have 91% or 91 kpsi. And so you fast forward to 14 years later, and so you've got for the lower dynamic fatigue, the crack has grown a little bit more, and for the higher dynamic fatigue, the crack has grown a little bit less. And then finally, some point down the road, the one with lower dynamic fatigue performance is actually broken, where the other one is still going. So this is a hypothetical illustration of how dynamic fatigue is used in a fiber, and you'll see this in a fiber spec. So the importance of dynamic fatigue performance is that installation contractors and Mother Nature don't always observe our rules, and so very good dynamic fatigue performance provides additional performance in the face of adverse conditions. And so a lot of cable ratings, so the numbers that we give for maximum installation tension will actually take into account the dynamic fatigue number in determining how much strain to put on a fiber. So we are nearing the end. One thing that I would like to highlight is that for anyone who is interested in seeing how fiber is manufactured, there is, if you go out to the OFS website or the OFS YouTube site, there is a fiber manufacturing video that will show you how fiber is manufactured. But in summary, the fiber is the network. There are many reasons that fiber is going deep into the network, and often to the home and in the home. There are several different fiber standards, G.652 and 657, primarily for outside plant. But one thing to highlight is that these standards only set basic performance levels, and so we would encourage you to really delve a little bit deeper, because just basic levels are kind of the lowest common denominator. And overall, as a manufacturer, we believe that the products need to perform much better than just the lowest common denominator. And so fiber performance is driven by many different things. So in optical performance, primarily attenuation and bend performance. And then with dispersions, chromatic and polarization mode dispersion. And then with mechanical performance, glass purity and coating and glass composition. And so with that, we are at the end of the webinar. If there are any questions, please submit those and we will respond back. I apologize, we're not able to do that live today, but we will address those. And there will also be a link to be able to see this presentation again. And thank you very much. We will have additional webinars that will be coming out on roughly a monthly to every couple of months basis. I think we've got one scheduled in November, and we'll have one in January. And so we will let you know when those occur. So thank you very much for attending, and that is the end of the webinar.